Chapter 1, Circuit Variables. In this lecture, we will be defining the concepts of power and energy and their mathematical equations. We will then relate how the passive sign convention correlates voltage polarity and current direction to a plus or minus sign for the expression of power. We are looking at two objectives: to know and be able to use the definitions of power and energy, and to be able to use the passive sign convention to calculate the power for an ideal basic circuit element. To review some mathematical definitions. Current. We defined electric current as the rate of charge flow expressed as dq over dt, where I is the current in amperes, Q is the charge in coulombs, and T is the time in seconds. Voltage. We defined voltage as the energy per unit charge expressed as dW over dQ, where V is the voltage in volts, and W is the energy in joules, and Q is the charge in coulombs. Let's define the concepts of power and energy. Although voltage and current are useful variables in the analysis and design of electrically based systems, the useful output of the system is often non-electrical. This output is expressed in terms of power or energy. Work is accomplished when energy is converted from one form to another, such as electrical energy converted to mechanical energy, or electrical energy converted to heat energy, or light energy, or sound energy. We see this energy conversion with our electric appliances, computers, stereo equipment, etc. Electric energy can be obtained indirectly and directly via combustion of fuels, such as from fossil fuel or coal-burning power plants, nuclear fission, which we have heard of through nuclear power plants. I'm sure most of us have seen wind turbines throughout our travels, which use the natural movement of air, and hydroelectric power, which uses the movement of water. Electric energy from solar radiation is becoming more and more popular, and of course we all take advantage of electrical energy from electrochemical reactions when we start our cars. Although the terms energy and power are used interchangeably, they are not the same. What is power? We can describe power in a number of ways. Power is the rate at which energy is converted. Power is the rate of expending or absorbing energy. Or power is the rate of doing work. How does this translate mathematically? All devices have limitations on the amount of power that they can handle. Therefore, in the design of circuits, it is important to perform power calculations. We know power is the time rate of expending or absorbing energy. Mathematically, energy per unit time is expressed in the form of a derivative, or P equals dW over dt, where P is the power in watts, W is the energy in joules, and T is the time in seconds. Likewise, work or energy can be found by integrating the function for power. The SI unit for power is the watt, named for James Watt, inventor of the steam engine. The SI unit for work or energy is the joule, named for James Prescott Joule, who shared the famous discovery of the conservation of energy. The power associated with the flow of charge follows directly from the definition of voltage and current, which allows us to relate power and energy to voltage and current, and our power equation becomes P is equal to V times I, where P is the power in watts, V is the voltage in volts, and I is the current in amperes. Therefore, power is a quantity associated with a circuit element and is the product of the current going through the element and the voltage across the element. We have to determine whether power is being delivered to the circuit element or extracted from it. This information comes from correctly applying and interpreting the passive sign convention. Power is positive when positive charges move through a drop in voltage and they lose energy. We see this in the top circuit element. Our current is entering the circuit element at the positive terminal, and there is a voltage drop. And the current exits the terminal at the negative side. In this case, power is being absorbed. Power is negative when positive charges move through a rise in voltage and they gain energy, as seen in the bottom circuit element. In this case, power is being extracted from the circuit element, and we say that the element is acting as an energy source, supplying or delivering the electrical energy to the rest of the circuit. So in this case, the current is entering at the negative terminal and experiences the voltage rise and gains energy. Excuse me, did I say energy? I meant current, or the charges gain energy through the voltage rise. To determine the algebraic sign of power, we must know the polarity of voltage and the direction of current. Let's take a look at some basic circuit elements which have different voltage polarities and current directions. Okay, in our first circuit element, charge is entering at the positive terminal of the circuit element, and it experiences a voltage drop and exits through the negative terminal. In this case, power is positive, and is being absorbed by the circuit element. In the second case, the current is entering at the negative terminal, and there is a voltage rise. So the charge is energized, and our power is negative, so our element is supplying. Okay, in the third example, charge is entering our circuit element at the negative terminal and is experiencing a voltage rise. So again, the power would be a negative value, and again, this circuit element is supplying energy to the remainder of the circuit. In our last example, the current is entering through the positive terminal and there is a voltage drop, so our power value would be positive and our element is absorbing energy. Okay. We use the passive sign convention when applying the equation for power. In this example, we covered it a little bit in the last lecture, but our current has a value of 4 amps when this polarity was selected and minus 10 volts. Now, the current is entering at the negative terminal, so the charge is going through a voltage rise, which means our power value is negative. And then V times I, so that's minus 10 times I, which is 4 amps. So in this case, power is equal to plus 40 watts. All right, in the second example, the polarity of the voltage is reversed and the direction of the current is reversed, and so the values are also reversed. So minus 4 amps and plus 10 volts. And again, the current is entering at the negative terminal and the charge goes through a voltage rise, so our power equation would be the negative V times I, which is 10 volts, and minus 4 amps. And the power is equal to plus 40 watts. So because the power is a positive value, it the element is absorbing energy. Okay, now both of these circuits and the polarity references on these circuits neither uses the active sign or the passive sign convention. Rather, this is called the active sign convention. And I like to use the passive sign convention. So how do I change this circuit so it uses the passive sign convention? Well, what I would do is either change the voltage polarity so that the current is entering the positive terminal and the charge goes through a voltage drop, or I change the direction of the current. So this first one, let's change the direction of the current, and that would make it minus 4 amps, because when we change the direction of the current, we have to change the sign. And now we have the passive sign convention. And the equation for power is P equals V times I. So, which is equal to V, which is minus 10 volts, times I, which is minus 4 amps, which is equal to plus 40 watts. Again, we could change the current direction, or we could change the polarity. So if we change the polarity of the voltage, and I should have done the opposite because I don't like to work with negative numbers. And it would give us the same equation, P equals VI, and all these negative numbers. So our convention is to set our reference direction for current such that the positive charge is moving across the voltage drop, which utilizes the equation P equal VI. So if our definition for current or voltage, let's say, is equal to 10 volts, and our current is equal to 4 amps, what would it look like here? This one's already set up in the passive sign convention, so our value here would be 4 amps, and our voltage here would be positive 10 volts. So we're good here. Now here, in the second example, our current is entering at the negative terminal. So let's change the current to this direction. So our current would be a minus I now, which is equal to minus 4 amps. And our voltage here is 10 volts. We're not making any changes to the voltage. All right, again with the third circuit, current is entering at the negative voltage terminal. So let's leave the current as 4 amps, and let's change the polarity of the voltage, which would then change the sign of our voltage to such. And the third one follows the passive convention, so the current is entering at the positive terminal. So we'll leave it at 4 amps, and our voltage is 10 volts. So since I changed all to the passive sign convention, the direction, we would use the same equation all 4 times. So power is equal to, in the first one, 10 times 40, or 10 times 4, which would be plus 40 watts. In the second example, power is equal to V times I, which is 10 times minus 4, so that would be minus 40 watts. In the third example, power is equal to V times I, which is minus 10 times 4, which is minus 40 watts. And in the third example, power is equal to V times I, which is 10 times 4, so power is equal to plus 40 watts. Okay. For assessment problem number 5, click on the link below to view the video. For assessment problem 1.7, click on the link below to view the video. Okay, let's review the concepts we have learned. We introduced the concepts and equations for power and energy, and we performed some power calculations using the passive sign convention. The equations defined for power is dW over dt, and work is the integral of power, and a second equation for power relating voltage and current is P equal VI. We solved some example problems which related the concepts, and that concludes this lecture.